All right, let's get started. How are you guys doing today? Can you all hear me?
Yep.
All right, awesome. So welcome to today's session. So this is after the midterm. So congratulations on finishing that. Hopefully our sessions were good for that. So yeah, I heard it was a bit difficult than the other exams. So hopefully the final will be a bit easier, but we can go ahead and start working on the project then. So this project is, I'd argue, one of the more valuable ones in this class because we're going to use a thing called linked lists. These are really important in industry because if you do apply to an internship, be it next year or something like that, a lot of technical questions will ask you about like how do linked lists work or just implementing functions using linked lists. So if you're to take away anything from this class, I'd say linked lists are probably one of the more valuable things. So before we actually go into the project, I want to just go over linked lists real quick because to my knowledge, you guys haven't actually gone over linked lists in lecture yet. So we'll go ahead and get started with talking about what a linked list is and the implementation of that. And then we'll go ahead and talk about the project as a whole. So any questions before we get started on that? And by the way, by the end of today's session, you guys should feel comfortable going ahead and tackling all of list.h. We're going to cover, so there's two parts of list.h. It's all one file, but the first part revolves around implementing functions for a linked list, and then the second part is going to be iterators. And those are a bit confusing, but hopefully, again, we'll go over like all the concepts today too. So it's going to be a lot of content today. So if you guys do get confused, speak up, ask questions in chat, interrupt me. I'm totally cool with that. Put questions in chat. And then afterwards, if you guys want to start coding the project, you can follow along in the slides. So hopefully this will be pretty productive. So any questions before we get started? All right, good stuff. By the way, we won't be covering the API portion today because this project is pretty dense. So today we're going to be focusing exclusively on like the linked list part, which is half the project. So let's go ahead and get started. So again, the goal of this project is to create an office hours queue. But the first thing we want to do is go ahead and work on our linked list portion. So let's go over what a linked list actually is. And for that, I'll go into Visual Studios real quick, just to kind of show you guys like what a linked list is all about. So a linked list, you can think about it as sort of a set of nodes. And those nodes are going to have three things associated with them. So a node's going to have a value. We'll call this datum. So in your guys' code, you'll see instead of it being int, it's going to be a type T. All that means is that we can specify what our linked list is going to be of. So type T can mean something like int, string, char, double, etc. So our linked list is going to be homogeneous, like kind of like the same type. So it's very analogous to arrays in that case, where everything in our linked list has to be of the same type. You can use like, instead of being like a primitive type, it could be like a struct or something like that. But for this class, you don't have to worry about that. I see you have a chat.
I don't think we can see your Visual Studio.
Oh, you can't? Oh, thank you so much. Sorry about that. Screen one. Can you guys see this now?
Yep.
All right, sorry about that. Okay. So yeah, again, in our struct right here, this is given to us in the starter code. So instead of, again, this will be a type T, but for this case, I'll have it be int, so it's just more clear to you guys. Again, we're going to have this datum right here. And this is sort of the value we have at a given node. And the way we want to create these linked lists is that every node is going to be connected to some other node, whether it's going to be through pointers. So let's say, for example, I'll go to these two in a couple of seconds. I first want to cover like how we actually create the linked list first. So a linked list, again, the nodes are going to be connected via pointers. So this right here, let's say we have a node. If we want to know what the next node is, we'll just go ahead and put the address of the next node in this thing called next. All next refers to is it just holds the address of the next node. Same thing as previous. This is just going to hold the address of our previous node. So right here, I created 3 nodes. Notice I used the new keyword here. We're going to allocate this on the heap. This is pretty important because in the project, whenever we create a new node for a function, we want to go ahead and use this formatting right here. This basically allows us to create a new node and work with it. So that means we're also responsible for deleting. So let's say we want to delete a node. I would just delete this node at a given address. So pretty straightforward, hopefully. So what I want to do here is link my pen out real quick. I'll draw out a diagram. And what we want to do here is we want to create a linked list such that we have some node. I'll use squares for these, by the way. And I want to have 1 connect to 3 and 3 connect to 5. This is our goal. And one thing I do want to cover real quick is the difference between singly linked lists and doubly linked lists. So a singly linked list, that basically means we don't have this previous. All we have is next. So our linked list will look like this. 1 is going to be a node, and its next is going to be this node. This node's value is going to be 3. 3's next is going to be the node containing 5, so on and so forth. A double linked list basically means we have this previous pointer, so we can go backwards. So 3's previous is going to be 1, 5's previous is going to be 3. Does it make sense so far? Okay, awesome. So let's say I wanted to go ahead, I made these 3 nodes, but they aren't linked yet, nor do they have value. So all we have right now is basically just 3 blocks like this. And what I want to do here is connect these and give them a value. So if I want to give a node a value, what I do here, let's say for node 0. So we'll call this node 0, node 1, and node 2. If I want to give node 0 the value 1, I'll just go ahead and say node 0 datum. Notice that this node's a pointer, so we have to use the operator, the arrow, like this. This allows us to access the datum of this node, and I'll set it equal to 0. So all I'm doing here, or I'll make it 1, sorry, because we have it as 1 right here. So all I'm doing here is just saying this node right here, I'm going to set its value or its datum to 1. I can do the exact same thing here. If I do node 1, datum equals 3, and then down here I can do the exact same thing for this. Node 2, dereference, datum equals 5. So that's how we set the values for these. So right now we have 1, 3, and 5. The next thing we want to do is actually go ahead and connect these lists. So to do this, we know that 0, its next is going to be this right here, the 3 value, right? To connect these lists, all we have to do is say node 0. So right here, we're looking at this node right here. I want to say its next is going to equal node 1. Like this. Sorry, let me go ahead and do that. Getting a compiler issue.
You only
You haven't initialized node 1 yet.
Oh, thank you. Yeah. I'll just copy these all over here real quick then. Thank you about that. Put these all right here. So yeah, right here I'm setting the values like this, so 1, 3, and 5. And then I'll go ahead and say node 0's next value is going to be node 1. So what I'm doing here is I'm saying the next for node 0 is going to be node 1. And here's the cool thing about this, right? Node 1 is going to contain a previous, a next, and a datum. So you can sort of see how the nodes contain 3 different things that can help us traverse our list. It's going to contain information, the datum, and it's also going to contain the previous and the next pointer. So far, all we have is this. We say 1 connects to 3. And to make 3 connect to 5, I'll go ahead and say node 1 next equals node 2. And now we have this. So far, if I want to, I can go from node 1 to node 3 to node 5. If we want to go backwards, let's say I want to have node 5 connect to node 3 and node 3 connect to node 1, we can use like the exact same process, except we'll use previous this time. So I'll say node 2 prev equals node 1. What I'm doing here is I'm basically just drawing this arrow. That just means that node 5's previous node is going to be this node right here. And I can do the exact same thing to connect 3 to 1. I can go ahead and say node 1 previous equals node 0. So perfect, we have our linked list set up. There are 2 things I want to mention real quick, and that is, what do we do with the previous right here and the next right here? So this is pretty crucial. For node 0 right here, the value of 1, its previous, we want to set as null pointer. The reason for that is because this is our first element in our linked list, and its previous value, we want it to be nothing. Because if we say go backwards, we don't want to go back to 5 because then we'll be in an infinite loop. If we go ahead and we have 1's previous be null pointer, that signifies that's the beginning of our list. So if we ever want to see, are we at the beginning, we'll just say, oh, is the previous value the null pointer or not? If it's null pointer, then we know that's our first element in the list. This is also referred to as the head of our list. And similarly, this is called the tail. In the project spec and in the project, they call this first, and they call this last. So you'll hear these used interchange. They mean the exact same thing. Head first, tail last, same thing. So if I want to set that, I can just go ahead and say node 0. This is our first node in our linked list. and I'll say its previous value is going to be null pointer. And then if I want to go ahead and say our next value and our last thing is going to be null pointer, I'll go ahead and I'll say node 2 next equals null pointer. And there we go. Our linked list is now created. So are there any questions about that process of me creating the nodes and then setting the pointers up and stuff? Any questions about that?
Yeah, I had a question about the struct itself. So
Yeah, sure.
I guess it's more of a conceptual thing, but so when you make a node, you start with a pointer to a previous node, like within the struct, but then wouldn't that previous node make a node within itself, which has a previous node within it? So how come that doesn't like continuously loop?
Oh, how do we have a node inside our node struct?
Mm-hmm.
Oh, so that's completely fine, actually. So what's happening is that this is going to be a node pointer. So all we're doing is we're holding the address of some pointer in here for a node. So it wouldn't be an infinite loop, because if I create this, right? Notice, actually, it's a good example of it, right? Since we're setting the previous and next of every single node, this is completely fine. And also, like for this right here, previous and next, we're setting them as null pointers. So don't think about this like recursion. Like there's no infinite loops happening here. All we're saying is that our node is going to have a node pointer like inside of it. So there's like no
Oh.
infinite loops.
Gotcha. So if it wasn't a pointer, then it would be an issue.
It actually wouldn't be an issue, because in that case we can just like not initialize some of them, right? Don't get hung up on it though. Like don't think about it too much. It's not that important. But just know that like all this is gonna do is just hold our address of the previous and the address of the next.
Okay, thank you.
Yeah, of course, of course. Yeah, and again, guys, like feel free to ask questions. This is like the entire project we'll talk about today is like this concept right here. So if anything's like fuzzy, like I'm happy to speak about it some more. Give you guys a couple seconds to think about some questions.
Would we delete all the dynamic variables like right after we create our linked list?
So you mean like allocating new and stuff?
Yeah.
Yeah. So whenever you create a new node, you always have to use the new keyword, because what we're doing here is we're just allocating this on the heap. And then let's say, for example, we'll talk about the function called pop front and pop back that basically just says, oh, pop front means remove this node right here. So all we have is 3 and 5 now. When we do that, we'll just go ahead and say like delete, like, let's say I wanted to remove 1 from our list. I have to go ahead and say delete node 0.
Right.
Like that.
Okay. That makes sense. Thank you.
Yeah, definitely. That's a good question, though. So one of the biggest tips I have for this project is make sure to run Valgrind on this, because roughly half the points for this part of the project are doing this correctly. It's really easy to do. All you do is just match up a new to delete. But if you don't do that, you'll like literally miss half the points, unfortunately. So make sure whenever you're testing your project out and stuff, go ahead and run Valgrind on it, because that's like a huge portion of the like project code for this, or the project points rather. And then I think in the autograder will also tell you like, oh, you passed Valgrind for this. So if you do that, you're all set. Just write some good tests. We'll talk about testing in a little bit too. But yeah, any more questions about this, guys? Again, this is a new topic to you all. It's like an entire lecture's worth of concepts right here. So if anything's fuzzy here, please speak up, because the entire session today is like predicated on these concepts.
Are linked lists in this class always going to be in structs?
Yes, they will always be in structs in this class.
Okay.
Yeah. And then I guess I'll talk about like some concepts, linked lists real quick, just so like we're on the same page here. Linked lists, they don't have random access. So think about an array. If I go into an array and I say like, oh, give me the value at like the 5th index like this, right? I can do that because my compiler knows that, oh, arrays are going to be sequential in memory, right? So I can use like point arithmetic and stuff. Linked lists aren't. In memory, we might have nodes scattered all throughout our memory. So that's why we have these pointers, right? Because they're not going to be sequential in memory. Instead, we're going to hold their addresses. And that is really useful, because that means we can like insert and delete like really fast. But it also means that I can't just say, oh, give me like our list at position 3. We can't do this because, again, our memory is not going to be synchronous. So that's why linked lists can be kind of bad. If you want to search a linked list, you have to search every single element, and you can't like randomly access. You either start at the head and then go to the next element, or you go to the tail and then go backwards. But notice how we can't just like look at 3. If you want to get to 3, it'd start at 1. and keep it going forward or go backwards. So linked lists are like, they aren't arrays. Don't try to think of them like arrays. They're like arrays, except for the fact that they aren't sequential in memory and they don't have random access. So they're pretty different, actually. So this is a new data structure. It's pretty different than vectors and arrays. But yeah, any other questions about this? All right, solid. Let's move on. So I'll get rid of this and then go back to the presentation. All right. So yeah, a lot of the stuff I just covered, but we'll go over it again. So in our implementation for list.h, instead of saying int like we did, they'll say type t. That basically just means that we can create a linked list of strings, we can create a linked list of doubles, ints, bools, etc. For testing purposes, I would just use ints because it's a lot easier to like debug and stuff. But if you want to, you can use linked list of strings, up to you. The node next, again, is going to hold the address of the next node in memory, and then previous will hold the previous node in memory. And this is what our struct looks like for our node. And again, we have visualization right here. This is, I think, the exact sample I used in the Visual Studio stuff. So we can skip this. We already covered that. But yeah, here's the syntax for it. It's like node 0, you create it like this with new node. Make sure whenever you create a new node, you'll see in the function we talked about today, we always want it, whenever we make a new node, we always say new node. If we're going to reference or like create a new node in memory, just always use new and then match it with a delete somewhere. All right, so let's go to our list functions. So a couple of terminology reminders. So first is going to refer to our head of our list. So going back to this example right here, we would call 3 the first. So this is going to be the head or the first of our list. That sort of means our list starts at 3. And that's defined because 3's previous value is going to be null pointer. So I'll have these arrows like dangling. Is that pointing to anything? That's intentional. So this means that 3's previous value is going to be null pointer, but 3's next value is going to be defined as being this node right here. Sitting over here, this is going to be the last. And that's defined because its next is going to be null pointer. So a quick like review real quick, or just a quick question for you guys. If I had a linked list of size 1, let's say I had 3 right here, and its previous is null pointer, and its next is null pointer. That means that 3 is going to be both the first and the last in our linked list. So that's a special case right there. And for a lot of these functions, we assume in the RME that our list is at least size 1. So don't worry about like a list of size 0 occurring in your code. They won't test that according to the RME. Some functions they might, but the majority of them they don't. They say assume a list of size at least 1. Okay, so let's go ahead and start out the functions real quick. So again, we have first and last, and then one thing I do want to talk about before we actually get into the coding is how do we traverse a linked list? So we have this linked list right here. Let me see if I can pull it back up. We have 1 points to 3 and 3 points to 5. How do we actually traverse this linked list to get information out of it? It's actually really similar to how we traverse an array using pointer arithmetic. So what we want to do here is we have this linked list set up, right? We already established this down here. If I want to, let's say, iterate from 1 to 3, 3 to 5, how do we do this? So this same structure holds for all linked lists, and this will hold for like a lot of our code. A lot of the functions we have to iterate through, so we can use this template. What I'm going to do here is I'm going to create a node pointer. I'll call this PTR, and I'm going to set this equal to my first. Now, in this case, we haven't defined first, but in our code, we will. First is just going to be our first node right here. So I'll say it's going to be node 0. So our pointer called PTR is going to be pointing to this node right here. If I want to iterate through this, what I want to do is say while PTR does not equal null pointer, go ahead and do stuff. What does that mean? So the way we define our linked list, we know that the list is over whenever our pointer isn't pointing something valid. Since this is null pointer right here, whenever we're pointing to 5 and we go next, it's going to evaluate to null pointer. And that means we're done searching our list. So let's say I want to go ahead and find the value 3. So I'll go ahead and put this in. Find if the value 3. So our goal here, we want to figure out, is the value 3 inside our linked list? To do this, we'll just go ahead and see if the value at our pointer, if ptr's datum equals 3, also like cout 3 is here. So we do that, but how do we actually increment pointer? Whenever we use arrays, we would say ptr++. That's not going to work here though. The reason being is that remember that nodes aren't necessarily going to be sequential in memory. With arrays, they were guaranteed to do that. But the nice thing is we have this next pointer defined. And next is basically the equivalent of saying this. So this is, so ptr++ is like saying, comment that out quick, ptr equals ptr next. So why does that work? So we know that ptr points to this node right here. The next node in memory is going to be this node right here. This node's next value is going to be 3. If I say ptr equals ptr next is just going to be 3, right? So all we're going to do is just say, instead of pointing to this node, we are now going to point to this node. And now we're pointing to this. We'll go ahead and say, is that the null pointer? It isn't. We'll go through and do it again. ptr equals ptr next is going to be 5. And now we're going to point to this node right here. And we'll do the exact same thing. After that, our while loop is going to terminate because the next value for 5 is going to be null pointer. So now we're going to be equal to this null pointer. And since ptr equals null pointer, we're going to break the loop. Does that concept make sense to you guys?
So you're essentially setting the PTR to be the pointing to the next node. That's all it is, right?
Yep, exactly. I'm starting off at the first node, and then I'm just going to go to the next node, and then the next node, until I reach the null pointer.
Got it. Thank you.
Yeah, of course. All right, so given that structure, we can actually do a lot of things with this, right? So our first function we talk about is empty. So if our list is empty, we know a couple of things. If, again, going back to this visualization over here, we know that we have a linked list like this, 1, 3, and 5. It's kind of a bad drawing, sorry. First, it's going to be defined by this 1 right here. And then last will be defined by this 5. However, let's say we have nothing in our linked list, right? What are first and last going to point to? Does anyone know? If we have nothing, if our linked list is just like nothing, what are first and last going to point to?
Null pointers?
Yeah, exactly. So if it's empty, can't we just check to see if first and last are the null pointer? That would be the best approach, in my opinion. Yeah, because again, first is going to point, and if it's of size 1, let's say we also want to write a function. Is it size 1? It's not a function, but it's a good exercise to think about. If the size is 1, we can think of that as first equals last. Again, if we have only one node, then that node's going to be the first and the last node in our linked list. So if the size is 0, that means that our first and last are going to be null pointers. If the size is going to be 1, that means our first and our last are the same node. And then otherwise, if we want to find the size of our node, of our linked list, sorry, we'll go ahead and we'll just iterate through our linked list and have some counter. And every time we visit a node, update the counter, and whenever we reach the end of our linked list, then we'll just go ahead and stop the loop and then return the value of our size. Does that concept make sense to you guys?
Can you repeat that, please?
Yeah, sure, of course. So let's say I want to find the size of a linked list for this example right here. I have 1, 3, and 5. So this format is going to hold for like all of our traversal questions. So on the exam, you'll use the exact same format. In interviews, you'll use the exact same format. It's a like really good format to use. All we're doing here, again, is we're just saying PTR is going to point to our first. I'll just put first right here. Because in your code, you'll put first here. One's our first. Whenever we iterate through our linked list, let's say I wanted to find the size of it. All I would do is say, okay, for every node I visit, just say the size, just increment the size by 1. And then I'll look at the next node and do the exact same thing. If the node's valid, we know it's going to be one more node to our linked list, and we'll increase the size. Because all we're doing here is we're going to visit one node at a time. If the node's valid, then we just add to the size and go forward again. To see if the list is empty, we can do that exact same function, and if it's 0, actually, yeah, we can use the exact same function, right? Because if our first is null pointer, then this will actually never like activate, right? Because if null pointer doesn't equal null pointer, that doesn't work. Because a list of size 0 is defined by first equals null pointer. And that should make sense, right? If we have nothing in our list, then our first should be undefined. Because first is signifying this is our first node or linked list. If we have no nodes, right, then first should be undefined. Same thing of last. So you can check either of these. Any questions about that? All right, good stuff. I'm gonna go ahead and shrink that real quick. But yeah, I'll go pretty slow today though, because again, you guys haven't learned linked lists yet, so this is like a lot to take in. So I understand it's pretty confusing right now, but by the time we're done, hopefully it'll all make sense. So again, for empty, we're just doing a validation check. We're just looking to see, is our first defined? We know that our first must point to something if our list has some size greater than 0. If first is null pointer or last is null pointer, then it would make sense, right, that our list is empty. So yeah, our traversal method, I use a for loop here too. So you can do a for loop or a while loop. This for loop is going to follow like a pretty similar format as we did in our arrays. So in our arrays, we'd always set it equal to, let's think about it, right? If I had an array and of size 3, we knew that array pointed to the first element. We're doing the exact same thing here, right? We're just saying we're going to point to our first element while our pointer doesn't equal null pointer. We're going to go to the next pointer like this. All we're doing here is instead of saying PTR++, we're just saying PTR equals PTR next. Intuitively, it's the same like idea behind traversal by pointer for our arrays. Instead of saying PTR++, we're just saying PTR equals PTR next. And I want you guys to think about, why do we have to do this? Why do we have to say PTR equals PTR next? And that's because our nodes aren't going to be like adjacent in memory, right? In arrays, we had like, oh, 1's next to 2 and 2's next to 3. In linked lists, it could be like, oh, our first node is here, but then like we have a bunch of like junk right here. Then we have our 3. So we have to have this PTR equals PTR next. So yeah, like for all the functions we write today, if you have to traverse, you just start your first node, and then if that node's valid, go to the next node. And then inside of here, you can go ahead and, do something with the information, right? Let's say, again, you're searching for some number. We can go ahead and do what we did in our code over here, which all we're doing here is saying, is the value at our given node 3? If it is, we'll output this. And then we'll just go to the next node. So can someone tell me, like, if we wanted to keep track of our size, what do we have to do in here? If we wanted to find our size, what should we do inside our list? Inside this for loop right here.
Increment the counter, maybe?
Yeah, exactly. So yeah, so why would that work?
The for loop would only run if it's not a null pointer, so then there's an item there, or a node there.
Yeah, exactly. That's great reasoning. So yeah, he's absolutely right. So if we're starting at the first node, and we know it's not the null pointer, that means we have at least one node that's good. And we'll go ahead and update our counter to reflect that, right? If our counter is 0, let me go back. I have to keep trying this example. I'm sorry, I should probably have a screenshot of it. 1, 3, and 5. So yeah, that's a good idea. Let's run with that. So we're starting at our first node. So I'll say PTR is going to point to our first node like this. And it's not the null pointer. So that means, hey, we have at least one good node. So we're going to update our size to be 1. And then we're going to go ahead and go to our next node, which is right here. We're then going to evaluate it and say, is this a null pointer? And it isn't. So then we're going to say, cool, size is actually 2 now. We'll go to our next node like this. And we'll do the exact same check. Is it the null pointer? And it isn't. So we'll go ahead and update this to be 3. Now here's a cool thing. We go to the next node. And we know that our last node's next is going to be null pointer. So this is going to fail, which means we won't execute this at all. And then we're done with the for loop. And our size is now 3. So yeah, it's a great idea. That's a perfect way to implement that, actually. Are there any questions about that?
I got a quick question about how you do PTR equals PTR next.
Mhm.
I get like how you're like kind of assigning them, but when does next change? Like, wouldn't it be staying the same?
Oh, that's a great question. Okay, so think about it this way, right? So I'll start at my first node, like this. So would you agree that PTR points to this node right here?
Yeah.
Okay, so what's this node's next value going to be? I'll call this node 2, just so we can be on the same page here. So what would this node's next value be?
The second node, 2.
Yep, exactly. So when I say this, PTR next is going to be node 2. So what I'm saying is our PTR is going to equal node 2. And now PTR is going to be node 2. So PTR is now going to be this node right here. And then we go back to this, right? And we have PTR's node 2. If I said, what's node's 2 next value right here? Because we've already established that we've already changed PTR to be node 2. And if I said, what's node 2's next value? It's going to be node 3. And I've changed that right here.
Okay, yeah, that makes sense now.
All right, yeah. Again, it's like really confusing because like it's hard to think about like, oh, we're just like constantly changing, like we're constantly updating our node. But if you think about it, right, we're just starting at PTR, we're going to the next node, and we're going to save that. We're going to say PTR is now going to be node 2. And then we go to the next node, which is going to be node 3, and we'll update accordingly. Any other questions about this stuff?
Hi, so I have a question. If we want to traverse the node like by the while loop, do we have to dereference the pointer like to like when it's false and maybe it's just 0? So in your code you use directly without the reference. So
Oh yeah, I should. That's my mistake. I'll update that real quick. Yeah, I should have the dereference right there. That's my mistake. Let me go ahead and change that real quick. Actually, good catch. Where is that? Yeah, I forgot about that. Sorry about that. Oh, there we go. But yeah, so these two do the exact same thing. Instead, like, yeah, we'll do stuff with our stuff and then update it. But these two, like, for and while loops do the exact same thing. But yeah, please ask questions, guys. This is a new concept to you guys, so I totally understand if it's a bit fuzzy. So if anything's unclear, I'm happy to answer that right now. Because once you get these concepts, the functions are really easy to write. It's just understanding, like, this is how most CS classes operate from now on, for projects at least, is that once you understand the concept, it's really easy to write. It's not like Euchre where it's like, oh, there's like 600 bugs I need to catch, like one edge case. For this, it's if you understand the concepts, the project, you can do it like super fast. But if you're sitting there coding and you're like, oh, how does this traversal work? The project's going to be really painful because you're going to be confused and just frustrated. So if you have any questions, like, please ask them now because I'm happy to answer them. Let's see what chat question. Wait, we can look at that real quick. Why do you need to dereference the pointer and while? So it's the exact same philosophy we had with the like traversal by array, right? Think about how we operated with string length, right? So on the exam review session stuff, we talked about what is string length. And what we're doing is we're just making sure that we're pointing something valid. So if I go ahead and do this, this will either evaluate to true or false. And it's the equivalent of just saying while PTR does not equal null pointer. It's the exact same thing. So I think intuitively the for loop's a lot easier to understand because like we see what's happening. We're starting at our first node. We're saying, is that node valid? If it is, go ahead and do stuff, and then we'll go to the next node. And if you ever get confused, think about like how we worked with arrays. We started at our first element in the array, and we went to the next element by doing PTR++. Instead of doing PTR++, all we're doing here is we're just saying PTR is equal to PTR next, which is going to the next node. Any other questions about like searching linked lists or like traversal? All right, good stuff. Okay, so yeah, size. We talked about this before, so good job for that. So push front, this is gonna be like one of our first like difficult functions, I'd say. So what we're doing here is, let's say I have a linked list. I'll go ahead and make this 3. It's gonna be a linked list of size 2, 3 and 5. So 3 is gonna be our first pointer, and 5 is gonna be our last pointer. And again, we could have like as many nodes as we want, but for this example, like intuitively, we'll just go ahead and work with 2. So what we want to do here is we basically want to go ahead and add a node right here. And we'll give it this thing called, we'll call it the value of datum. Let's call it dat for now. So what I want to do here is create a new node in memory and link it up like this. That's our goal here. So I think I have a visualization for this. Perfect. Okay. So let's assume over here I have like a bunch more nodes that aren't shown, right? Like this list keeps on going, but I didn't draw it because it'd be a bit more confusing. So this is our first node right here. What I want to do here is I want to append this thing called temp to it, right? Temp's just going to be our new node we're adding to our linked list. What I want to do here is, first of all, create the node in memory. That's our first step, right? We want to go ahead and just create this new node. So in our coding over here, we talked about how do we actually make a new node. All I did was just go ahead and make a node. We can call it temp, and I'll say it's a new node. So if I wanted to do that, I'd say node pointer temp equals new node. And that'll go ahead and create a new node in memory. From that, that's great, right? The next thing I want to do is go ahead and give it its value. So in our function, we're passed in the value of the node we want to give it to. So that's great. I can go ahead and do that. I can say temp datum equals the value we passed in, which is datum. Let's go ahead and define up here. Datum equals like 5 or something. Perfect. So now we give it the value of datum. So I'll go ahead and like show it like this. The next thing we have to do is go ahead and connect the list. And this can be a bit confusing because we have to alter what things point to. So a lot of people get confused because they're like, oh, I need to go ahead and update everything over here. Well, actually we don't, right? Because this list is going to be the exact same for everything over here. The only thing we're changing is how temp and first are related. If we want to put temp into our list, all we have to do is just go ahead and say, okay, temp's next is going to be this right here. First previous is going to be this, and temp's previous will be null pointer. And then our list is complete. But the process for that can be a bit like hard to understand, so we'll go through this for a little bit. So over here, I made a couple of steps. So we go ahead and we create our new node on the heap. We did that. And then we have to go ahead and change what our values, what our nodes point to. So over here, we have our original list, And again, there's going to be other nodes over here. I just didn't draw them for simplicity's sake. We'll go ahead and create our new node right here. Notice how first previous is going to be null pointer. We want to change that. And in our definition, in our class, first and last are defined. So whenever we work with a list for a given list, right? First is always going to be defined as something, null pointer, or it's going to be some node. So whenever we work with this list, we know that first is going to refer to this node right here, and then last will refer to something over here. That's really important because what we can do is say, oh, we have our node first. We want updates previous to be this new node, right? So I can say first prev, and then I want to make that equal to temp. And what that does is instead of first prev being null pointer, I'm just extending this arrow to go to temp. So that's great, right? Same thing, I want to go ahead and say temp next is going to be our first. And I've created this branch right here. So now our nodes are connected and everything's all good. There are two things we have to do still. We need to make sure that temp, its previous is null pointer. Because what we're doing here, whenever we say push front, we are making temp the new head of our list. So we have to go ahead and say temp's previous is going to be null pointer. And we also have to say first equals temp. And now we're all done. A couple of things I want to cover real quick. The order in which you do this does actually matters. So let's say, for example, I went ahead and I said temp is going to be our first. That's an issue, right? Because now I've lost this node in memory. I can't access it anymore. And that's an issue. So what we want to do here is go ahead and set it up so that these nodes are connected like this, and then change what node is going to be first. So again, going through the process again, we have our original list. We're going to create a new node in memory. We have our list right here. We're going to go ahead and update first previous to be temp, temp's next to be first, temp's previous to be null pointer, and then last but not least, we want to make temp our first node. That's important because whenever we do another function on this, we want to make sure that whenever we reference first, it's going to be the head of our list. Any questions about this? Yeah, go ahead.
Hi, I'm wondering why we need to assign first to the temp, because when you use the assign, signal, you means that you copy the first information to the temp, but the first information is only the datum, next, and previous.
Yeah, sure. So what's happening here is that if you look at the code for the list.h, first is just a node pointer. So it's going to be like node pointer first. And this defines, let me get rid of that real quick. Okay. So first is just going to be a node pointer, right? This node is already defined in memory, right? First is some node in memory. When I say node first, that's just referring to the first node in our list. It doesn't actually have it's not allocated on the heap. It's just a reference. So whenever I go ahead and I change first to go ahead and go to temp, that's just a reference, right? I'm just saying first is going to be our first node in the list, and that's going to be defined by temp. So I'm not actually copying anything over. I'm just saying the address of, so the value of first is going to be the address of temp.
Oh, I get your point, but whether we need to just copy just like the next, the third one to the first, and the fifth one to the third.
Oh, why are we not copying over the datum and stuff?
But I mean that you make the temp become the first pointer, then the first will become the second, and the second will become the third, right?
Yeah. So, but we don't actually define second or third. We only care about first and last, right?
Oh.
Yeah. So, sorry, go ahead.
Oh, why you only care the first and?
Yeah, it's a great question. So remember in our linked list, let's say I have 3 elements, right? if I add a fourth element right here, like this, let's draw these arrows real quick. If I draw those, I'm saying, okay, first originally is this node right here. Whenever I add that in, I'm saying, no, first is going to be this node right here. We can always access the next node and the next node, the next node. We only actually care about the first and the last node because we can access any other node from those nodes. The first node's important because that denotes the head of our list. And whenever we want to start searching our list, right? We talked about searching the list over here. We always start at our first, right? So we want to make sure that we have a good reference to our first element or our first node so we can start at the beginning of our list. So we technically don't need to have anything for second because we can just do first next to get second, right? But we can't, like, it doesn't make any sense to keep track of second because we can get that information really easily. And then think about if we had like 100 nodes in our linked list, right? It seems pretty weird to have like 72, right? That's not like very intuitive. It would be very inefficient. So if we just keep track of our first and last, we can just go ahead and traverse our list that way. And also remember why first and last are important. First is important because first previous is going to be null pointer. So that tells us that's our beginning of our list. Last next is going to be null pointer as well. It tells us it's going to be the end of our list. So we technically don't actually care about like the rest of the list whenever we update this, right? All we're doing is just changing our first to be this and linking these two nodes together. We're not actually going to go ahead and like change any of the rest of the nodes in here. First is just like a reference. It holds the address of our first node in memory. It's not going to like do anything else besides that. It's just going to say, if you want to access the first element on our list, just use this pointer right here. Same thing as last. Does that make sense?
Yeah, thank you.
Yeah, of course.
I got two things real quick.
Yeah, go ahead.
So my first thing is kind of an understanding. A lot of this project is just kind of trusting that your nodes are in memory and like you're not really like not kind of like not with arrays. You're not gonna know where they are exactly. You're just gonna like trust that they're there.
Yeah, because every node's going to be linked together, right? We have node pointers in our struct. Let me go back to that real quick. Yeah, so like we have like pointers in here that'll keep track of the organization of our list, right? So like think about it this way. It's like sort of like a guarantee. Whenever I say go ahead and add a node to a list, like add a node to the beginning of our list, right? You're going to assume that every node that is like next, everything in our list is going to be defined properly. So yeah, absolutely right.
Gotcha. Okay, that makes a bit more sense. And then
Okay.
my second thing was, since we made the new temp, don't we have to delete it before the end of the function?
So that's a great question. We actually don't, right? Because we want to keep that node in our list. If I have 3 nodes and I say, let's add a 4th node to it, right? It doesn't make much sense to go ahead and delete it, right? We want to keep that node there because the entire point of that function is to add it to our list. Now, there's a function called pop. We'll talk about that in a couple of seconds. And that basically says, okay, go ahead and find the first and delete it. That's where we're actually going to delete the list or delete that node. So we don't actually want, because, Again, it's a great question because I know like I've talked about like, oh yeah, match every node to delete, but we want to keep that information in our list until we don't need it anymore. So if we have a list of size 3 and I say push front, I add this node, we're happy. If I say the next function we'll talk about is called pop back, and that basically says, okay, go ahead and remove the first. No, I can't control Z. Unlucky. But yeah, pop back or pop front basically mean remove the front node in our list, and that's where we'll use delete.
Gotcha. Thank you.
Yeah, of course. So the next function relies really heavily on the understanding of how this works. So again, any questions, I'd appreciate them. Like anything, like I'm happy to answer anything. So if anything's confusing, like please let me know. All right. I'll assume you guys all understand this, so we can move on. But yeah, just quick note, like, is there a bad to ask questions? I keep saying that because this entire project builds upon itself. So if this is a bit fuzzy, the next function will make even less sense, and then after that, the next function will make even less sense. So just make sure you have a good understanding of this. So if anything's like unclear or anything, like, please ask me. I'm happy to answer that. All right, solid. So let's talk about pop. So push, this went ahead and we added a node to the beginning of our list. And by the way, in your code, there's going to be a thing called push back. That'll be the exact same process, but instead of us inserting at the beginning, we'll insert at the end. So it's like the exact same process, except instead of like working with first, we're going to work with last. So the code should be pretty similar. In scope, you're just working with different nodes instead. You can follow the exact same process on the slides. All right, awesome. So pop, what we're going to do here is we're going to remove a node in our list. And we have pop front and pop back. We'll talk about pop front because this one's going to follow the same trend we did for push front. So pop front, what we do here is, let's say we have a list of size 4. We have this, 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 and this. Let's say I have 1, 3, 5, 7. I have nodes 0, 1, 2, and 3. This is going to be our first node, and this will be our last node. So if I said I want to get rid of our first node right here, remember that in our like struct definition of our class of our list, we have first defined, and first is going to point to this node right here. Our objective in this function is to go ahead and remove this node, and then go ahead and say, okay, the first is now going to be 3, and that's the objective of our function. So it's sort of like the reversal of what we did before. So there's 2 steps for this. We first want to go ahead and delete our first node. We then want to update our next node to be the first. And again, if that node exists, we want to go ahead and do that. So if our list is of size 1, we just want to go ahead and delete our node, and then we're done. So the easiest case is, okay, our list is of size 1 and we pop front. All we do is delete our node and we're done. But obviously, most linked lists will have more than one element in it. So how do we actually deal with that? So I want you guys to think about, how do we know what node's going to be next in our list? What node in this list should be next for our, like, what should be our new first node? If we have these 4 nodes, out of these 4, removing this one right here, which node should be our new first node?
The next node, which first was pointing to.
Mm-hmm. So this node right here, 3.
Yeah.
Yeah, exactly. So how do we get that? How do we get that information?
Go to the first node and then find the next one, I guess.
Yep, exactly. So we have first. Remember, we always have first available to us, right? First is going to be defined in our functions, sorry, in our class. And it's assumed that first is always going to be accurate, right? So if I want to go ahead, I want to find the next node, right? So the second node in our linked list, I say first next. And that'll say, great, that's going to point to right here. So we have first that points to 1. And if I say first next, that's going to give me the node right here. So we know that first next should now be our first. So does that idea make sense to you guys, how I got this node? All right, good stuff. So I'll assume you guys understand that. So from here, we've gone ahead and we've accessed this node right here. After we have that information, we can go ahead and delete this node right here. We can go ahead and just say delete first. And that'll go ahead and we'll just do this. That's now gone. What we do have, though, is we have this pointer. I'll say PTR equals first next. So we now have inside pointer, we have the address of this node, which is the next node in memory. From that, I can go ahead and reassign that to be first, right? Because I've saved this right here in memory. I said PTR is equal to first next, and then I deleted first. So I can go ahead and say our first node is now going to be PTR. So I'll run through this again. What I did is, let me get rid of this. I'll go through it again so it makes more sense. We have first right here. And the first step is I want to go ahead and identify what should my next node be in my linked list. What should the new first be? So I'll go ahead and say, let me fully define it real quick. I'll say node pointer, call it PTR, equals first next. Yeah, go ahead.
Oh, I just wondering, just like, should we check whether it exists before?
Yeah, absolutely. That's a great question. You definitely should. So what you can do is, it technically doesn't actually matter, but it's great intuition though, because let's think about our process, what we're doing here. I go ahead and say node pointer equals first next, right? So let's say, for example, our linked list was of size 1. If I go ahead and I say, so this linked list is size 1. Our first is going to be this right here. If I say first next, what do we get out of this? We get null pointer, right? And if we go from size 1 to size 0, our next is going to be null pointer. And then we go ahead and we assign first to this value right here. So that means we're all good, right? Because we're saying our list went from size 1 to size 0. And even though it doesn't exist, we're going ahead and we're just saying that our first is going to be null pointer. And that should make sense, right? Because if our list is size 1 and we remove this, our first should be null pointer.
Oh, so actually we don't need to check this because assign first to the null pointer is okay.
Yeah, exactly. First being null pointer is completely fine. That just means our list is empty.
Okay, thank you.
One thing you might want to do though is, if that is the case, like after you run your function, if first is equal to null pointer, go ahead and set last to null pointer, because last will if the list is of size 1, last is still pointing here, and that could be an issue. So what you should do in your function is go ahead and cover what we did here, and then check to see, oh, is first null pointer? If first is null pointer, then you can go ahead and just say last equals null pointer. And that's like it's this case where it's size 1. Otherwise, you can work normally through it. That's a great question though. So yeah, right here, notice how we aren't actually saying node PTR equals new node. We only use new node when we want to add a node to our linked list. Here we're just creating a temporary value called PTR, and we just want to save the value of 3. Because what we want to do here is just save the value that should be our new first, because we're going to delete this eventually. And we just want to keep this value of what our new first should be. So I have node PTR equals first next. So PTR is going to point right here. Once I have that value saved, I can go ahead and delete first. And once I delete first, this goes away, and that node's now gone. The next step is going to be setting first equal to PTR. Now, one misconception here is, doesn't delete first remove the variable first? It doesn't. Since first is a pointer, what it does is it's going to remove the data at that location in memory. So since first points to this node right here, if I say delete first, all I'm doing is just removing all the information here. And now I'm going to say, instead of pointing to nothing, go ahead and point to PTR. And we said we want PTR to be our new first, because we're moving our first, and we want the next thing to go ahead and be our first. And the last thing we want to do is go ahead and say first previous is null pointer. And a quick explanation for one thing right here. What happens to 5 and 7? Do we have to update anything there? What do you guys think?
Those
Yep,
are, yeah.
Yeah, exactly. You don't have to. So yeah, perfect. So all we have to do here is update these two nodes. We're saying we want to get rid of this node. We want to make our new first pointer be at 3. Any questions about this?
I just have a mini question. When you delete first, you said that like it doesn't actually delete like the variable, like the pointer first, but you just delete like the datum that first is pointing to. Is that correct?
Yeah, it's actually going to delete the node that first is pointing to. So first, technically, it's so in our code, it's defined like this. In the starter code, it's defined node pointer first, like this. So notice how first isn't a new. If first were a new and we said delete first, then yeah, that would delete the node. Instead, first is a pointer, right? So all we're doing here is saying first points to this right here. If I delete first, what I'm going to do is I'm going to say delete that node in memory. First is just going to keep track of what our first node is on our linked list. So I can go ahead and just go ahead and reassign first after that. We're not like, we can still reuse the variable first. When I say delete first, all I'm doing is just getting rid of the node it points to. So it's getting rid of that node. So in this case, it would get rid of the node 1 that has the value 1, sorry. So it'll delete the datum, it'll delete that node's first, or sorry, it'll delete that node's previous pointer and the node's next pointer.
Gotcha. Okay, that makes sense. Thank you.
Yeah, of course.
So when you do the first equals PTR, what does that exactly do?
That's a great question. So what's happening here is first holds the address of a node in memory, right? We've gone ahead and we said node pointer PTR equals first next. That was our first step. First next is going to be the address of node 1 right here. So when I say first equals PTR, I'm just saying first is going to have the address of node 1 in memory, as opposed to having the value of node 0 in memory.
Got you. But what exactly does that, or how does that help us again?
Oh yeah, it's a great question. Okay, so that helps a lot actually, because what we want to do here is we're getting rid of our first node in our linked list, but we want to update where our first points to. Because remember that first always refers to the start of our list. And since we're removing the first element in our list, we want to go ahead and say our list starts at 3, not 1 now. And first is defined for like a single linked list, right? So for all the nodes, for every for a single linked list, right, there's only one first and one last. So all we're doing here is saying instead of our list starting at 1, we're now going to start at 3.
Okay, that makes sense. So would the order be first you do the first equals PTR, and then you'd set the first prev equals null pointer, and then would you delete first, or like what's the order with that?
Yeah, it's a great question. The order does matter, definitely. So what we do here is we go ahead, we first want to figure out what our new first should be. So PTR is going to be a placeholder for that. When I say our first step is going to be setting node PTR equals first next, that's going to give us the value of this node's address in memory. It's going to give us node 1 right here. First is still pointing to this right here. First is, we haven't changed first yet. Notice that, right? All I'm doing is saying, I'm going to create this temporary pointer called PTR. And I'm going to find the value of first next, which is going to be this right here. Okay? After that, I'm totally fine to go ahead and say delete first. The reason being is that the only purpose first had for us initially was I wanted to go ahead and figure out what's our new first going to be, right? Whenever we delete this node right here, where should our list start? And we found it right here. So after that, I'm going to delete first. And since first still points to this node right here, I can go ahead and delete it. After that, we know that PTR is pointing to what our new first should be, right? So I'm going to say first equals PTR. That's saying that our first element in our list is going to be this right here, which evaluated to node 1. After that, I have to go ahead and update this because we know that every single first node, so for a first node is defined that its previous value is going to be null pointer. So I just update that right here. So the steps would look like this.
Okay, got you. So the delete first only gets rid of the like the address. It still exists, correct?
Yeah, so first still exists, but we're deleting the node.
Got you.
So first is going to point to a node, right? So think back to our coding example, right? Over here. Let me get rid of all this real quick. So you see right here how I created a node right here, like new node. If I go ahead and I say node pointer first, like this, and then down here I say first equals node 0. If I say delete first, like this, what it's going to do is that will delete node 0, like that. But I can still say first equals like node 1. Let's say I want to do that. That's still fine. If I did delete, let's say, for example, instead I did delete node 0, then I'll just delete the node entirely. Since first is just a pointer to it, I'm totally fine to go ahead and just delete first. What that does is it'll just erase the value. Oh, it'll just delete this node right here in memory.
Okay, that makes sense. Thank you.
Yeah, of course. All right. Any other questions? But yeah, here's a visualization for this. So we first go ahead and we create a node pointer that holds the address of our first variable. So all we're doing here is just saying we're going to contain the value first. We're next going to find the value of our next node in memory, like this. We then delete first, like this, and then we update our pointers accordingly. Actually, I have a mistake here. Delete our first. Sorry about that. But yeah, any questions about this, guys? All right, so that covers it for the first half of linked lists. So now we can take questions like just kind of about like linked lists in general. So the next portion is going to be iterators, and those are ways we can work with our linked lists. So I want to make sure you guys understand these functions entirely. So if you have any questions about them, like I'm happy to answer anything. So like anything to talk about today, like any questions about that?
So if we're trying to pop the last element, it would just be the same concept, but now PTR would be the previous one from the last, and then the last next one would be the null pointer, correct?
Yeah, exactly. Perfect. No, that's exactly right.
Okay. Cool.
So yeah, we've talked about push front and pop back, or sorry, push front and pop front. There are two other functions called pop or push back and then pop back. Those two follow the exact same concepts, but instead of us working at the first, we're going to work with the last instead. But yeah, it's the exact same concepts. And it should be the exact same process, but again, we're working at the last instead of first. Okay, awesome. Okay, so we've defined our nodes. We want a way to organize these. So a constructor for our list class is basically the default constructor is going to set our first null pointer and our last null pointer. So if I go ahead and create a list, right? If I just say I want to make a new list, let me get my pen out real quick. If I create a new list and I have no values in it, then it should be defined as our first being null pointer and our last being null pointer. That should make sense, right? If our list is empty, we're creating a new list that's empty. So that means that our first and last should be null pointer, because that's the definition of an empty list. Okay, and the last thing we have to be worried about is clear. So clear is essentially going to go through and take a list of some size, and it's going to go through and delete every element in it. So it seems a bit tricky at first, but recall that we've already defined what pop front does. So pop front, what it does is it goes ahead and it deletes this node right here, and it updates this to be our first. right? We've already done that. So what if we just did this until our first was undefined, right? So let's think about what's going to happen here. Let's say I have a list of size 3, and our first points to this. If I go ahead and I call pop front once, what's going to happen? If I call pop front once, I delete this node like this, and then first now points to this, and this is now null pointer. If I call it again, I delete this node like this. First now points to this, and this is now going to be the null pointer. Or sorry, I deleted the wrong one. It should be like that. And then once I call this again, first is going to point to this value's next node, right? This next node is just going to be null pointer, because this is technically our last as well. So this is our first and our last node in the linked list. Whenever I delete it, first is now going to point to null pointer. We delete that node, and first is going to be null pointer. So the idea behind clear is we want to recursive, or not recursively, just iteratively, we want to keep calling pop front or pop back until our first is defined as null pointer. Does that idea make sense to you guys? Like how that works intuitively? Because we know that pop front is going to remove one node at a time. And it's going to update first to be the next node in our linked list. So if we keep calling pop front, it's going to delete one node at a time until we reach the null pointer. Since the last node in our linked list, oh, we got like, okay, we had like 10 people just join at once. Oh, welcome. Okay.
He's explaining list.
Yeah, list. Okay. Yeah.
Yeah.
So like 16 people just joined at once. So yeah, I'm talking about clear real quick. So essentially for clear, I'll re-explain it, I guess, because a lot of people just joined. So we already defined pop front and pop back. So pop front, again, what we did was we had a list of some size. For this example, we use a size of 3. And what we're going to do here is, remember, we have first defined as this right here. It's going to be our first node in the list. What pop front does, it will remove the first element in our list. So when we call pop front once in our list, it's going to go ahead and remove this node right here. And we'll go ahead and we'll point to this node instead. We want to keep calling this until first points to null pointer. When does that actually happen? Well, that's going to happen once we pop one more time. First now points to this. And we're going to go ahead and pop one more time. Remember our function we defined pop back, or sorry, pop front. We want update first to be our node's next. Since this node's next is null pointer, first is going to evaluate to null pointer. And after that, when first is null pointer, that means our list will be empty. So you can go ahead and do this either pop front or pop back, but the idea is we want to delete one node at a time and just see if like our list has any elements in it still. Any questions about that? All right, awesome. So remember, for copy all, this is a copy constructor. And this essentially will just copy the values from one list to a list given by this. So remember that this is going to be an implicit pointer, and this refers to the list we are working with right now. So I think we use this in Euchre as well, but for all intents and purposes, this is the exact same process as we did with the this pointer in Euchre. The way this works is that we want to go through and copy node by node until we reach the end. So remember our algorithm for actually iterating through a linked list. We want to start at our first pointer like this, and we want to make sure that our pointer is pointing to a valid node. We can check this by saying if pointer is not null pointer, we can go ahead and go to the next element like this. And inside of here, we want to do something with our datum, but in this case, we just want to copy over the node entirely. So we can go ahead and create a new node in memory, transfer the datum, and just make sure the nodes are equal in value. When I say that, I basically just mean that make sure the first and the, sorry, not the first, the previous and the next are going to be equal whenever you copy over. So we're just iterating through a given list, and we're copying over the values and the values of next and previous. And for this, we can also just use this dot pushback because we already defined pushback, right? That's the easiest way to accomplish this.
Can you explain that again?
Yeah, sure. So what we're doing here is, this is a copy all, and basically we're just given a list called other. And our objective of this function is to go ahead and copy the nodes from other to our implicit pointer called this. And this basically is just defined by our local list. And what we want to do here is we basically want to take one node at a time and copy it over. Remember that push back or push front, what we're doing here is we're just taking a node and we're adding it to our linked list, right? So we can go back and look at our definition for it over here. So push front, we went ahead and we had a datum value, right? And what we did was we created a new node in memory and we gave it to a value and we add it to our linked list. So what we can do here, right? If our objective for this function is to go ahead and just copy over node by node, right? We already have a function that does this for us, right? Push front and push back will automatically add nodes to our list, right? That automatically creates a new node in our heap and it'll give it a value, right? So if we're copying over from some defined list, right? We want to copy over all the contents of some list called other to this. All we have to do is go ahead and call it push back or push front, depending on where we start on our list, and add those values to our list, because this will basically do all the heavy lifting for us. This will create a new node. And it will give it a value, datum. And if we want to iterate through our list called other, we can just use this right here. We can start at the first of other, and we can traverse through it until we reach the end. And every time we are at a node that isn't null pointer, we want to go ahead and call either push back or push front, depending on like where you start in the list. So if you start at first, you want to go ahead and push back, right? Because the way this works, right? Let's go ahead and draw a diagram. Let's say I have a list of size 3. Like this. And I want to copy this over to a new list. So our new list is going to be empty. And this list, I'll call it other. That's how they define it. It's called other. It's defined, let's say it's a list of size 3. Our new list is going to be empty. I'll call it this. What we're doing is we're starting at the first of our list called other, and I'll call pushback on it. Recall that pushback will basically just add a node to the end of our list. So if I call pushback on our first node right here, what that does is it'll add this value to our list called this. I'll get these values real quick so it makes more sense. And this will then go ahead and our function called pushback, that will go ahead and it'll create a new node on the heap and it'll give it the value datum. So if we just call pushback on that like node with that value, it'll go ahead and add it to our new list. We'll then go ahead and we'll say our pointer, PTR, is now going to point, it was originally pointing at 1. Now it's going to point to 3. If we call pushback on 3, remember that pushback is defined as saying we're going to add this node to the end of our list. And the end of our list is right here. So we'll go ahead and we'll just add 3 right here. Yeah, go ahead.
So I just want to make sure you mean that pushback do just like create a new node in this list, right?
Yeah, exactly. I'll create a new node. Because remember, push front we go back to this, like go back to that slide, we didn't cover push back, we covered push front, but the idea is the exact same, right? Push front, it'll create a new node in memory and it will append it to the beginning of our list. So we actually call the keyword new in here to create that new node. If I'm calling push back, that's going to create a new node and place it at the end of our list. So yeah.
So the pushback function, like if the list have no node or have nothing, the pushback function on the first one should be just like the previous should be no.
Yep, exactly. Yep, that's a great point. So in your function, you should definitely account for that. If you're calling pushback on an empty list, then you definitely have to account for that.
Oh, I get. Thank you.
Yeah, of course. So yeah, right here, we're just going to go through and like look at a given node and then call pushback on our this pointer. And that'll go ahead and it will add that value to our list. And then we just update PTR to go to the next node in that list, like this. And if we call pushback on 5, that'll go ahead and we'll just add 5 to our list like this. Remember that pushback will automatically do all this for us. So once pushback works, we can just use it and assume it works because we've already tested it and stuff. Pushback will go ahead and it will correct our pointers for us and it will do all the heavy lifting for us. All we're doing is just calling this function until we reach the end of our list. Yeah, I see we have 2 hands raised. Go ahead.
Yeah, what is this again? I don't really understand that. What
yeah,
is...
so it's called the implicit pointer and it's basically just what we're operating on. So this is if we call like copy all, if we're calling it on this, it's basically just our local list.
The local what?
Local list. So if we call it like this, it's called the implicit pointer. And essentially it's like, think back to copy constructors, it's like initialization, right? If I'm creating a new list, it's just like I'm operating on a new instance of the list. And the word this isn't required, it's implied. That's what's called implicit, but I think it just makes more sense to have like this there. So like if it doesn't make any sense, like essentially like I just put it there so it like makes more sense. But it isn't needed per se. It's implied in the compiler. But it does help us because we're copying a list over to a new list.
So we basically could have just done pushback of like the pointer.
Yeah, exactly.
The loop. Okay.
Yeah, you don't need this implied. Yeah.
Thank you.
And I saw we had one other hand raised, so go ahead. All right. So before we go into iterators, I just want to make sure that these functions make sense to you guys, like intuitively what's happening here. So if there are any questions about like pushing, popping, iterating, all that fun stuff, happy to answer those now.
I had a question for copy all.
Yeah, sure.
So do we like initialize a new list for this or?
You don't have to necessarily, because when we call pushback on an empty list, it'll go ahead and create our first pointer for us. And in pushback or push front, however you want to do it, you should handle that case where the list is empty.
Okay, thank you.
Yeah, of course.
I also have another question. Sorry.
Yeah, no, go ahead. It's all good.
I joined late, but would you explain what next does? Does it basically just increment the pointer to the next node?
Oh yeah, was PTR next to you right here?
Yeah.
Yeah, that's a great question. So again, let's say we have a list of size 3 like this. And I go ahead, let's say PTR is pointing to first. In this case, first is pointing to our first node right here. We have these values right here. So I say PTR equals first. So PTR is going to point to this. So if PTR points to first, right? Question for you. What is the value of PTR next? If PTR points to 1, what node is going to be PTR next?
Would it be 3?
Yeah, exactly, right? So why is that?
Because I think it's just incrementing the pointer towards the next node within the list.
Yeah, so the way we define this node, right? So if I call this node 0, right? Whenever we create this node in memory, I said like node pointer, we'll call this 0 for now. 0 equals new node. And then once I made this list before, right? This list, 0's next equals 1. We'll call this 1 right here. We'll call this 0. So these are just names for nodes I made in memory. So since PTR points to this right here, it points to first, right? This is it's kind of confusing, but PTR holds the value of this node in memory, right? Because PTR equals first, right? First holds the value of the address of this node right here. It's going to hold the value of 0. 0's next is defined as 1, right? Because we've linked it up like this.
Yeah.
If I say PTR equals PTR next, right? PTR is going to point to this node, and PTR next is going to refer to whatever this node's next value is.
Okay. So basically you said it equal to first. Is there a name for what next would be set to? Like, is it second, or would it just kind of just be a place within the memory?
It would just be a place in the memory. Yeah, exactly. We haven't defined that. So there's a case where it could be null pointer, right? So let's say, for example, my list is of size 1. If I go ahead and I call PTR to be pointing to this, PTR next would be null pointer because this list is of size 1.
Okay, cool. And then how would it know to like that the first belongs to that node when you initialize the pointer to it?
Oh, because so we'd actually define first, right? In our functions, whenever we set up a list and we say like, oh, I want to add I want to create a new list, right? I'll set first equal to that first node, right?
Awesome.
And then from that, we just assume that first is pointing to our first node in memory.
Awesome. All right. Thank you so much.
Yeah, of course. I see I have a chat question. So my chat still bugs, so I have to stop sharing whenever I look at chat. Have we gone over iterators in class? No, you guys haven't. So again, that's why this is gonna be kind of a long session today, and it's gonna be kind of confusing because I'm covering like 2 lectures and a project in 2 hours. So I don't expect everything to be crystal clear to you guys, but I just hope that the intuition's there. So you can like refer back to the slides or come next week and we can go over some more stuff. But the idea is by the end of today that you should have like a baseline understanding of linked lists and iterators, and then the function should be a little less daunting. But yeah, all this stuff should be new to you guys, which is kind of unfortunate because I think 4 days before the project's due, lecture goes over pointers, or sorry, they go over linked lists. So it's a little late for that. So this should be a good head start, hopefully. But yeah, any other questions about like lists in general and stuff? All right, we can go forward now. So iterators. These might be new words to you guys. I'm not sure if you've used iterators before, but basically iterators are a pointer type. And in this case, let's see if a chat question. Sorry, I have to keep stop sharing screen when I look at it. Or can I access the slides? I can link those real quick, actually. They're always going to be within the SI folder for EECS 280. That's linked in the email every week, but I can just go ahead and put them here for you guys. There you go. Yeah, of course. Let me start sharing again. All right, perfect. So an iterator essentially is going to contain the value of a node, right? So an iterator is just going to hold the value of some node. This is pretty important though, because the way we want to work is that we want these iterators to hold the value of some node, not just the first or the last, but it can hold the value of any node in memory. So let's say, for example, again, I had this list of size 3. Before, I had it like this. 1, 3, and 5. Those are just the datum values, by the way. So we have node 0, node 1, node 2. Originally, if I wanted to get to, let's say, node 1, I would have to start at node 0 and then find the next value, right? Same thing if I wanted to go to the value of 3, I can start at this node right here and find its previous value, right? Because first and last are going to be defined. Like this. The idea behind iterators is that they're going to help us traversing our list. So an iterator is basically going to hold the value of some node in memory, and it's going to allow us to do operations on it. This is pretty important though, right? Because what we can do with this then is we'll see there's going to be functions that are going to be like, oh, go ahead and give an iterator that points to this node right here, go ahead and delete that node. So instead of just working at the front and the back, we can now work with stuff in between. So iterators are really helpful tools that allow us to do that. We can also define operations in iterators. So let's say I create an iterator. We're going to define this thing called the plus plus operator. So we're going to sort of be able to think of it like pointers, right? Like in arrays, we could say ptr plus plus, and that will go ahead and go to the next element. In iterators, we can define this plus plus operator, and that will allow us to go to the next node in memory. So iterators just make our lives a lot easier in terms of like looking through a list. And they do what they say, they're iterators, right? They allow us to iterate over the list. And that's like the very like shallow definition of it. In lecture, we'll talk about a lot more, but just for now, let's just consider this basic understanding. So our iterator class has one element in it. It's going to be a node pointer called node pointer. So again, our iterator is just going to hold the value, the address of some node in memory, right? So that will allow us to work on other nodes that aren't the first or the last. So there are a couple operations we're going to define. So plus plus. Think back to pointers. If we were going to search an array and I did something like, oh, ptr, like int star ptr equals the start of our array. And if I did ptr plus plus, if I had an array that's like this size right here, we'll call it ARR, with like values 1, 2, 3, 4, and 5 in it. If I said ptr equals ARR, right? ptr would point to this. If I did ptr plus plus, ptr would now point to 2. What we want to do here is we want to have this plus plus operator work the exact same way, but for linked lists. Now, since linked lists aren't going to be synchronous in memory, right? We just said that they don't necessarily have to be. The nodes can be disjoint in memory. So it's not guaranteed if we do like some ptr plus plus that the node will be there. What we want to do here is we want to go ahead and define this plus plus operator so that given an iterator, we want to get the next node in memory, right? And this should be straightforward because let's say I have node ptr. And remember that this is going to be a node pointer, right? These are all nodes. This will point to this node right here. If I say node ptr plus plus, what I want to happen is I want this, instead of pointing to this, I want to now point to this. That's the idea here. So how do we actually accomplish that? Well, we know that node pointer points to a node. And we know that nodes have 3 things with them. They have a previous node, a next node, and a datum. So if we wanted to get the next node in memory, we can do the exact same idea we had in our traversal, right? Can't we just say node ptr equals node ptr next? That's sloppy. And what we're doing here is we're taking our iterator that was originally pointing at node pointer. We'll just say for right now that let's assume that node pointer was pointing to this right here. If I call plus plus, I want to change node pointer. Instead of pointing to this node, I want to point to the next node in our list. And that's basically just doing this. We're just saying our node pointer is now going to point to the next element. And this can get a bit confusing because you're like, whoa, how do iterators have access to this? Remember that our iterator is just a node pointer. So whenever we do this, that's completely fine because we're assuming that our iterator holds the value of some node. So I can go ahead and call plus plus, and all that's going to do is just do this. Does that concept make sense to you guys? All right.
So node plus plus, does that
Yeah.
does that execute the line that you just like erased?
Yeah, so what we do basically is we would create an iterator. So I'd say like iterator I. And we'll talk about constructors in a couple of seconds, but we'll basically have it point to some node, right? So let's say we have iterator I, and we'll say this points to first. So down here, we can see our default constructor. It can be set to null pointer, or we can set it to some node passed in. So again, I could just set an iterator, and I can pass in first. And that'll make it so our iterator is going to hold the value of first in memory. So then if I say I++, what this does is, let's say my list is like this. I have 3 things in it. I have first, which is what I points to. If I say I++, instead of I pointing at this, it's now going to point at this, like this.
I see.
Yeah, and that code right there just defined it for us.
I see. And how would you implement, or I guess, or like how would you implement the constructor that just like points the node to a specific value in the list?
Yeah, so if we pass in something that isn't, like we pass in a value like this. Yeah, so here all we're doing is we're passing in a node, right? And we know that node pointer is going to hold the value of a node pointer, right? And we're passing in a node pointer. So what do you think we do? If we're passing in a null pointer, or sorry, we're passing in a node pointer, and we want node pointer to point to that node, right? We'd have something like node PTR equals, what do you think it would equal in this case? If we're passing in a node pointer, when it makes
that node.
Yeah, so we would just put the node here, right? We don't need the address of the node because remember that the node is going to be a node pointer that we're passing in. Right? If we're passing in a node pointer, the address of something, and we say node pointer equals that, we're saying node pointer is going to point to that. So let's say let's say for example, for the non-default, if I passed in, we'll call this node 0, node 1, and node 2. I'll draw the arrows real quick so it's a bit more clear. Let's say I went ahead and I passed in this node, right? If I said, I want node pointer to point to this, we'll call this node 1. I would literally just say node pointer equals 1. Because there I'm saying, I want this iterator to hold the node pointer of this node right here.
Right.
As opposed to my default, if I said iterator I, that's going to point to null pointer. And then I can go ahead and say, I want I, if I pass in first like this, so iterator I, I'll say like first, right? That'll then create an iterator that points to first. If I just say iterator I, it's going to point to null pointer, which isn't much use to us, unfortunately, because we want to actually work in our list. So if I say iterator I and I put in first, that's going to have our iterator start at this right here. Our iterator is now going to point to first, and we've defined plus plus. So if we do plus plus, it'll go ahead and make it so that our node, or sorry, our iterator I is now going to go to our next node like this. And then it's going to stay there. If I call plus plus again, it'll go ahead and it'll go to the next node. If I call plus plus again, it'll go to the next node, which doesn't exist. So I will be null pointer then. So this is really useful because what we can do now is we can traverse our linked list by using the method I showed over here. Or if you want, for testing purposes, or just like other functions and iterators, you can use plus plus.
So is node pointer a private, or I guess a local variable for the non-default constructor?
Yeah, so node pointer is going to be defined for all iterators. So in our iterator class, we only have this. We have node pointer. That's our only variable. So every iterator is going to have, it's going to hold the value of some node pointer. That could be null pointer, it could be first, it could be any node in our linked list.
And the parameter that's being passed to the constructor of the iterator is the node we want the node pointer to point to.
Yep, exactly. Or it could be nothing. We could just go ahead and say iterator I, and that would create an iterator that points to null pointer.
Perfect. Yeah, that makes sense. Thank you.
Yeah, of course. And then, so yeah, go ahead, Avi.
Yeah. So how do you define the iterator? So do you just do like iterator I is equal to like node pointer or something like that?
Yeah, we go ahead and we just say iterator I, and we just go ahead and put parentheses like this, and then we'd pass in some node. Or we can go ahead and just say iterator I, and that'll just make it point to null pointer.
Oh, so you pass in like for example, the first node. So would that just be like node pointer or something?
Yeah,
That
so
you defined
yeah.
before?
So like right here, I can just say iterator I like first, like this, and I'll define an iterator that points to first.
Oh yeah. Well, yeah. Oh yeah. First is the iterator, and then you said like incrementing. So do you just do first plus plus or something? Or
You would say like node pointer equals node pointer next. Right? Because node pointer. Yeah. Because think of it this way, right? Even though it's a different class, we're still working with a node pointer. And our nodes are defined as node pointers. So if I just say node pointer equals node pointer next, that will just go ahead and go to the next node in memory. Or not in memory, sorry, like in our list.
Yeah. So then why'd you do I plus plus then?
Because we're just defining right here.
Yeah.
So for our iterator class, we're going to define this. That's one of the functions you have to define is how do you define the plus plus and minus minus operator?
Oh, got it.
So it just makes our lives a lot easier, right? Because instead of us saying like every time like, oh, node pointer equals node pointer next, we can just go ahead and say like I plus plus. But we have to define that first, right? Because we're using a custom data type, we want to go ahead and say, what does plus plus mean?
That makes so much more sense. Yep. Thank you.
Good stuff. Yeah, go ahead.
I just want to make sure that for the iterator that we already have a list of node, and the iterator just want for us to access these nodes simpler, right?
Can you say that again? Sorry.
I mean, before the iterator, is that the case that we have already a list of the node, and we want to access each node easier by the iterators?
Yeah, so iterators just make it easier for us to access our nodes. So technically, we can access any element in our linked list without iterators, but it's a lot more painful because what we have to do is we have to start our first or our last, right? So let's say I have a list like this again, and I don't have iterators. If I want to go ahead and access this middle node right here, that's going to be pretty annoying because what I have to do here is I have to go ahead and start at our first and I have to go to our next. With iterators, I can go ahead and say iterator I, and I can pass in the value of this node right here. It just makes it a lot easier for us to traverse our list and work with certain values in our list. And for example, right, let's say I wanted to go ahead and specify a function that says remove this node from memory. Without iterators, that's pretty difficult, right? However, with iterators, it's a lot easier because I have access to these operators plus plus, minus minus, etc. So you're right when you say like iterators make our lives a lot easier. They don't allow us to do anything like new that we couldn't. It just makes it a lot easier to think about and to work with.
Could we only just access the element by iterator through plus plus and minus minus? Is it possible just like we want to access the fourth one and we do something like array to point to the fourth?
Oh, how do you, so if you want to get like exactly the fourth element, so we actually can't do that. So we can get to the fourth element, but we can't just say, oh, I want to get exactly the fourth element in constant time. The reason being is that, remember that these linked lists aren't going to be synchronous in memory. With an array, they were. So arrays were defined like, oh, we have this block of memory reserved for an array. And our array is going to be a fixed size. Linked lists, we can't do that, right? Because remember that we can remove nodes at any time. We can add nodes at any time. So our linked list is constantly growing and expanding in all directions. So if I wanted to get to the fourth node of linked list, I would have to go ahead and call like plus plus 4 times. There's no like better way to do it because linked lists, there's drawbacks to using arrays versus linked lists, right? Linked lists are really good because we can add stuff really fast, right? If I want to go ahead and add something to the front, it's like super efficient and super like fast. For arrays, it's a fixed size. We can't do that. Vectors, same story. Linked list stuff, I want to access like a middle element. It's pretty tedious because I can't just access the middle element. I have to like go PTR plus plus. I have to do iterator plus plus a bunch of times until I get to that element. So that's the issue we have there.
Oh, so we could not just like access the first one directly.
Yeah, you can, but what you have to do is you have to like again do plus plus 4 times. You can't just like get the fourth element by saying like iterator 4. That doesn't work, unfortunately.
Okay, thank you.
Yeah, of course. I see you have a chat question. Let me read that real quick. Is it possible to get started on list functions before the iterator functions? Yeah, so you want to go ahead and do list first, then iterator. I should have mentioned that before, but yeah, definitely go ahead and do list, then iterator. You can go ahead and do all of the list functions like push, pop, copy, empty, size, all that stuff without doing iterators. So if iterators are so confusing to you guys, again, ask questions, but you don't need to do iterators just yet. They aren't needed for the first half of this session.
And each of those functions we're writing in list.h.
Yep, exactly. So yeah, iterators are going to be in list.h, and so are all of these functions right here, like pop and all that stuff. Size, push, copy all. Those are all going to be in list. So we're iterators. If you look at the starter code, the way it works is that the first like half of your code is going to be list functions, and then the other half is going to be iterator functions. All right. So does this make sense to you guys so far? Like the concept of iterators and how they work? My chat's still broken. 1 second. Yes. All right. Good. Good. Okay. So there are 2 functions I want to talk about, and then we should be done for today. So the functions are going to be erase and then insert, and then some testing stuff after that. So erase, what we're going to do here is instead of erasing, so think back to push, or say pop. So pop was we want to remove the first element in our list. That was pop front. Pop back was we want to remove the last element in our list. Erase is saying, given an iterator I, we want to delete the node at a given iterator. So let's say I want to delete the second node in the list. How do we actually even do that? So what I'd do here is I'd create an iterator I. So I'd say iterator I, like this, and I'd pass in first. So that'll give me an iterator. So I is going to point to first. If I then say I++, that'll have me point to this thing called target, which happens to be the second node in our list. So does that make sense how we got I to point to target? So I'm now accessing the second node in our list. And this is the example. This function isn't saying delete second. It's just saying delete I. So I'm just saying how you'd actually get I in this case. But in this case, we're just passing in iterator I. And what we want to do here is we want to go ahead and just get rid of target. And we want to fix our nodes such that first, next now points to this right here. And this node's previous points to first. In this case, this list is of size 3. Obviously, a list could be larger than 3, but for this example, I have 3. So I have first, which is our first node, target, our second node, and last, our third and final node. So again, the list won't always be of size 3, so we're not like literally saying first, next equals last. I'm just saying for this example, this list is of size 3. Does that make sense to you guys, what we're doing here?
So like so the erase function takes in an iterator?
Yep.
And
it takes an iterator, and given that iterator, we want to remove that node that the iterator points to. So in this case, iterator I, for this example right here, is going to point to target. I call that node target, and that's going to be our second node in the list. What we want to do is we want to go ahead and delete target and fix these pointers so that first next is going to point to this, last in this case, and last previous, instead of pointing to target, it's going to point to first. So you see how we're basically just going to go ahead and like literally delete this and extend these arrows.
yeah.
Okay.
So why would we need to increment I when the iterator already points to the
Oh.
node that wants to be deleted?
So you don't have to. It was just me showing how to actually like get I for testing and stuff. You don't have to do that. You're just given I. Like if they're testing it, they'll like find some iterator and pass it in. I'm just saying, how would you actually like get an iterator that points to target? Does it make sense?
Could you repeat that? Sorry.
Yeah, sure. So I'm just saying, like, you don't have to do this. It was just an example of me showing like how can you get an iterator that points to target? Like, how could you actually get this if you were to test it? They'll pass an iterator I, obviously, so you don't have to do any of this. I'm just like trying to show an example of like how you'd go ahead and like get that iterator.
Okay.
For your function, you don't have to do that, so don't worry about it.
Okay.
All right. So again, we have this list right here. Our iterator I is going to point to target like this. And our goal is to go ahead and delete target and fix our pointer so they work like this. So what are our steps? So what we have is we have iterator I, and that points to target. What we can do from this is we know if we delete target, we have to fix these connections right here. We need first, next to point to last in this case, and this arrow's backwards, and last previous to point to first. So intuitively, it's sort of like we get rid of this node and we just continue these arrows like this, right? That's the idea here. The implementation is a bit confusing because, okay, how do we actually link this up properly? So let's go through it step by step. If I want to go ahead, and I think I have a visualization over here. Do I? Okay, I don't. So what we want to do is, before we delete target, let's go ahead and fix our pointers. So question for you guys. When we delete target in this case, what should first next point to? It's not going to point to target, but what should it point to?
Last.
Yep, exactly. So we know that I is an iterator that points to target. How can we get the value of last from this iterator?
Target next.
Yep, exactly. So from that, we can go ahead and get last. So, and how do we get the value first? We can do target previous. So in this case, we can get like target.node pointer previous, and that'll give us the value first, right? This right here gets us the value of our first right here. So the thing before target. And some things get a bit confusing. So I hope these things make sense to you guys. I say that this caller is first. So this right here means we were accessing first. This block right here is getting us the first node, and this block right here is getting us the last node. So notice that right here, I'm saying target.node pointer, because this is a right here, target's an iterator. Say target.node pointer previous. That gets us first. And I say next. So that seems really weird because it's like we're going previous then next. So that'll give us target, right? Well, what I'm saying here is that I want target node pointer previous. So I want first like this. That gets us first. And I'm saying first next equals target.node pointer next. And that evaluates to last. Does that linking concept make sense to you guys, what we're doing here? We're basically accessing first, and we're saying, I want firsts next to be last. And again, I want to make it clear that this is for an example of size 3. You're not going to go ahead and say like first and last in all cases. I just did this example because it's pretty easy to like digest, but it's just a coincidence that it's a size of 3. So go ahead, Avi.
Yeah, so why can't we just say like first and last? Why do we have to do the like that implementation like that?
Oh, because yeah, again, this list is of size 3, right? So this will only work for size 3 if I do this. If it's like size 4, let's say for example, this wasn't called last, this is called like something else, and then I had last right here, right?
Yeah.
Then that won't work because then I'm basically skipping this node right here.
Yeah. All right. And then what does target dot node pointer mean?
So that accesses the node pointer that our iterator is pointing to. So
Oh.
I guess I can change this to I probably, so it'll make more sense. The iterator is called I. So
Mhm.
I dot node pointer, and that'll get us the value of target, and I'm saying target previous.
Okay.
And that'll get us first. Yeah. So if that logic makes sense to you guys, what we're doing here, we're basically going to go ahead and get the value of our first node right here. So node 0, like that. I'm saying its next node should be this, as opposed to target. Does that linking make sense to you guys? Okay. So I'll assume it does. So let's go backwards. Let's go ahead and do the second example. Let's say I want to go ahead and instead of saying, this arrow's backwards, sorry. So last, right here, so the next thing after target is going to be called last in this case, right? For this example, it's going to be called last. If I want last previous to point to first instead of target, what do I do? Well, if I say target.node, so target is going to be this node right here, .node pointer. That'll give me the node pointer for this right here. It points right here. And I say next. That'll give me the node right here called last. After that, I'm saying, okay, for this node, this is last. We can all agree on that, right? I'm now going to say previous, because I'm saying last previous equals target.node pointer previous. So this block right here, this refers to first. And this block right here refers to last. So notice the previous right here is just denoting I want last previous to point to first. See, I have a question in chat. 1 second. Let me look at that real quick. Why do we do target.node pointer when target is a node? So remember that target, in this case, is actually going to be an iterator. And an iterator is an object, not a pointer. An iterator just has a node pointer associated with it.
So would that node pointer for the iterator be publicly accessible? Like
Yeah, so yeah, exactly. So for an iterator, every iterator is going to have a node pointer associated with it. And that node pointer is going to be null pointer or some node in memory. And yeah, it's going to be publicly available to that iterator.
Okay.
So yeah, for all of these iterator functions, you can use that.
So basically, iterators are like objects that like they are associated with like either the null pointer or some node in the list.
Yeah, exactly. It's a great way to think about it.
Okay.
Yep.
Thank you.
Yeah, of course. Any other questions about these iterators for erase?
Do you have to do both the like both ways, as in the next prev and then the prev next?
Yeah, unfortunately you actually do, because remember that our objective here is to basically fix these connections. So the steps should be like this. Our first step should be fix the connection. So whenever you work with linked lists, like on the exam, in interviews, in this project, etc., whenever you want to modify a list, before you delete anything, you want to make sure you make the connections proper. So what does that mean? That basically means go ahead and make it so that first, its next points to last in this case, and last points to first like this. And again, I want to make this clear because I realize it's a bad example. I'm saying first and last because this list is of size 3. If your list is of size 4, it wouldn't be first and last. It would be something else. I'm just using first and last for this example because it's easy for a list of size 3. So I want you guys to like make sure you're actually coding that you shouldn't be using first and last when you're coding the function erase. You should be using stuff like target.node pointer previous next, right? Because it's not guaranteed your list will be of size 3. This is just a pretty good example to use because it's intuitive to understand. So like, please, when you're coding, remember that we won't always have first and last here. This is a good example. So I want to stress that because I don't want you guys to code and like have it not work. So yeah, we fix the connections like this. So once that is done, we can go ahead and then just delete this node. And then we establish our connections like this. And then we delete our iterator like this. Because deleting our iterator holds the value of a node pointer, and that node pointer holds the address of target. So when we say delete the iterator, we're basically deleting this node. I see we have a chat question. Should erase be coded to work on the first and last, or is it assumed we'll only use it on edges? That's a great question. You should code it so that it will consider edge cases. So if you call erase on the first or the last, then yeah, definitely go ahead and code that in. It's a great question. So I think it's pretty easy to handle. All you have to do in that case is, just delete the node and then make the previous node the last. If you're delete, let's say for example, I called erase on last like this. If I call erase on this right here, all I do is I delete this and I make this last and make its next pointer point to null. And if I were to call it on first, I would delete first, make target my first, and I would go ahead and say its previous null pointer. Otherwise, if it's in the middle, go ahead and just do this algorithm right here. Oh yeah, or if it is on the edge, push pop front and put pop back. You know, those work, so we can always reuse those. All right, any questions about erase?
I have a question with the requirements.
Yeah, sure.
So it says I is valid, dereferenceable iterator. Does that mean it's I should not point to a null pointer?
Yeah, exactly. It's assuming that iterator I is going to point to some node in your list.
Okay.
So yeah, you never have to worry about like, oh, what if like I delete the null pointer? Like, don't worry about that. It's always going to pass in some valid node. But again, your list could be of size 1, size 2, size 8, could be any size greater than 0. So yeah, definitely account for the edge cases where I think someone in chat said this, where what if you're on the edge? Then basically go ahead and just call pop front or pop back because those already account for the edges. All right, our last big function for this project is going to be insert. And insert, what it does is instead of deleting a node, we're adding a node. Fun. The difference is that we're adding the node before the iterator. So let's say, for example, I have a list of size 2. I have node first, I have node last, and I'm going to call insert on last. My objective should be I want to add in this new node called target. Let's call it target for now. And I want to fix these pointers. So instead of like this stuff right here, I want to get rid of these. I want first next to point to target, target previous point to first, target next to point to last, and last previous point to target. That's the objective here. So how do we actually do that? Well, we first want to go ahead and create our new node. So we'd just go ahead and say like new node, we'll call it target or anything you want really. We then want to go ahead and update our pointers, fix the pointers like this, and then copy over the data that's passed in. So visually, the way this looks, and I think this one's a lot easier to understand visually, we have our list like this. We first create our node. So right here, we have 2 nodes that are connected. We have first and last that are connected for a list of size 2. So let's make that clear. Size is 2 in this case. We first create our new node like this. Our second step is to go ahead and have target have its previous point to first and target's next to point to last. So what's the pattern here? How can we actually do this like reliably? Well, we know that we're inserting target between first and last in this case, right? Because our list is of size 2. What we do is have target next point to the iterator we passed in, because it said we want to insert target before our iterator. So before implies that the next thing after target should be the iterator we passed in. So since our iterator is last, we're going to go ahead and say target next equals last. And then what should target's previous be? Well, we know that last previous is going to be first. So we can go ahead and set target's previous equal to last previous. And then we have this connection all set up. Does this stage make sense to you guys, what we're doing here?
Could you explain the parameters that are given for this function?
Yeah, sure. So we're given 2 things. We're given an iterator and some datum t. And the iterator basically says we're going to insert this new node with datum t, or datum of type t before our iterator I. So in this case, we are inserting, for this example at least, we have a list of size 2, and we're going to go ahead and call insert on last, which means that we're going to put our new datum, our new node, between last and first.
Right, yeah, that makes sense.
Okay, cool. And again, this list is of size 2, so it just so happens that we only have 2 nodes, and they're called first and last. This won't always be the case. Again, our list could be of like size 8, and we could insert in between it. So don't code it to where it relies on first and last. This is a helpful example, so it makes more sense. Like the last example where we only had 3 elements in our list. Yeah, go ahead.
I'm wondering why we just like copy the datum at the end of this.
Why do we copy the datum at the end?
Yeah.
Oh, you can do it at any stage you want. You can go ahead and copy the datum first. So first you create the node, and then you can copy the datum. It doesn't matter when you copy the datum, but the order in which we link up the list does matter. So you can copy datum like after step 1. I just said like last because it's more convenient. It's up to you though. You can copy the datum whenever you create the node.
Okay, I got it. Thank you.
Yeah, of course. I see you have one more question too. You can
Yeah. So there would be like 2 edge cases if the target was like if you want to make target the first one and target the last one, right?
Yeah, exactly. So let's say I said I made my target first. What should we do in that case?
Do you want to make the first previous the target?
Yeah, so you can do all that work, but what function did we make that did that for us?
Pop back, right?
Push front.
I mean, yeah.
Yeah, you got it though. And then similarly, if I call it on last, what should I do?
Push back.
Yeah, perfect. Exactly.
All right.
Yeah. So that's the idea, at least, is that in a race, we went ahead and we called pop back and pop front if we were on the edges of first and last. And then for insert, if we call it on first or last, we want to go ahead and actually for insert, we can't insert at the end, right? Because we always insert before it. So if I called insert and last, then we would never actually have to call push back, right? Because we're always inserting it before the iterator. So if you call it on first, then it makes sense that we're adding a new node right here. But if I call it on last, we're adding the node right here. Does that make sense?
Would it be possible if the iterator is pointing to a null pointer, then it might be pushed to the end of the list?
That's a great question. I would have to read the spec again. There might be something about that. After the session, I'll look over it with you. That's a great question, though. I'm not 100% sure, though, but that would make sense to me. But again, I'm not sure that's a feature or not. Okay, so then step 1 was we had the list. We create the node. Step 2 is we want to link up target to first and last. Notice how these connections are still here. We have to update those. So in step 3, we have to go ahead and have this node's next point to target and this node's previous point to target. And that's pretty easy to do, right? All we just say is, okay, the iterator we're pointing to, we passed in last as our iterator. So we're saying our iterators previous is going to be target, and our iterators previous is going to be first. That's next is going to be target. So we can say like our iterators previous is going to be first. So we can say like iter prev next, assuming iter's a node. And that's assuming that's a node. And then we're good. And that's all linked up now. But yeah, any other questions about like insert and delete? All right, good stuff. So before we conclude today, I want to go over some testing strategies. This project, I think, is pretty easy to debug because there's like 3 main cases. So either you're going to work with the beginning of a list, an end of a list, or somewhere in between. So we thought about edge cases where it's like, oh, well, if you go ahead and call like insert at the beginning or you call erase at the end, consider those edge cases. Consider lists of size 1 and 2. Size 1 because first and last are the same, and size 2 because first and last are the only 2 nodes in our list. So those are pretty important cases to test. Iterators are really good to work with here because, again, you can like get access to any node you want and then call functions on it. So you want to see if you're deleting properly, go ahead and like run valgrind. Valgrind is really important. So valgrind will essentially just check your program, make sure that you aren't leaving anything on the heap or that you aren't deleting anything you shouldn't. So if valgrind, you pass it and your functions work, you're good to go. But this is like 20 points out of the main suite. So it's like half the points on the private test cases for list. So please make sure this works because this is a lot of points right here. But yeah, iterators are really helpful. These can help you test out your functions like really easily. And that's basically it. So if you guys have any more questions, I'm happy to stick around for a couple more minutes and answer those. But otherwise, good luck coding, and I'll see you guys next week.
Thank you so much. This was really helpful.
Yeah, of course. Glad you liked it.
Thanks, Max.
Yeah, of course.
Thank you.
Yeah, of course. And then I'll stop recording. If you guys want to stick around and ask more questions, I'm happy to stick around for a couple of seconds.